All right, students, we are continuing in our introduction to regression. I cut this lecture in the middle because it was a little mentally taxing, and I know it can be a bit overwhelming. So we're continuing on in our introduction to regression. We stopped after introducing the idea of a population equation, a sample equation. We've talked about our dependent variable, our explanatory variables. We understand what our coefficients alpha and beta are, what they're capturing, and that we can subject them to hypothesis testing to see if they're statistically significant. But what we haven't done at this point is actually talked about how we create estimates. So we're going to talk now about a technique called ordinary least squares. And this is abbreviated often as OLS. And ordinary least squares, or OLS, is simply a method for estimating the coefficients in our regression equation, those alphas and those betas. So let's talk about what OLS is doing. Now, OLS, as we said, it's just one type of regression estimation, but it's probably the most common, and it's the only one that we're going to use for our purposes. But if you had an interest in this, there are all kinds of things you can learn online about more sophisticated regression techniques. We like ordinary least squares because it produces the best linear, unbiased estimates. The best linear, unbiased estimates. In other words, it's blue, best linear, unbiased estimates when meeting a certain set of assumptions. Now, in the graph to the right, our data is the circles. So each circle is an observation. Remember, we're just in a world of simple regression. We've got an X and a Y, for example, gender and salaries, or we might be talking about absences and test scores. But our data is the circle. So we've got a data set here. And what OLS is doing is that it's fitting the best line, creating a prediction, to the data. So you see this red line that's being fit kind of right through the middle of those observations. So it's fitting the best line or best prediction to the data. But what do we mean by best in this case? What do we mean by best? Well, we notice here that each observation is just a little off the line, right? There are very few observations that literally sit right on the line. Each observation's a little above, a little below. And these are the residuals. It's our estimates of the error. Remember that little E sub I term at the end of our equations? And we said E sub I. The sub I told us that we'd have a little bit of error for each of our observations. Well, that's what we're seeing right here. We have a little bit of error for each of our observations. Some observations are above the line, some are below. Some are positive, some are negative. And so when we say that we're going to fit the best line, what we mean by that is that ordinary least squares wants to minimize these errors. It wants to fit the line just so that it can minimize those errors, those little vertical, little yellow lines that go up and down. Those are designating my errors. I just put two of them on the graph so you could see them. So OLS fits a line that makes residuals as small as possible, So the line that's the best is going to be the one that makes the residuals, that error, that distance from the line, as small as possible. But here's the deal. We've got some that are positive, some that are negative, and we don't want the positive to offset the negative. So we're going to square the values. And you've seen us do that before in other lectures. So again, if I took 4 and negative 4, do we agree that equals 0, which suggests there's no error? So the problem is if I just add together all the residuals and try to minimize it, positive and negative residuals are going to offset each other. And then it makes it look like there's no error. And that's not going to work. So can you remember what we did to solve that problem? Well, we squared the values, right? And so instead of 4 and negative 4, when we square them, it becomes 16 and 16. Now they're not going to offset each other. 16 and 16 means there's residuals of 32, just for an example. Now, ordinary least squares, as we just said, is going to fit the line that makes the sum of the squared errors. You understand why we have to square them, right? Because of the negative 4, positive 4 offsetting each other. So it's going to fit the line that makes the sum of the squared errors as small as possible. And that's why OLS is referred to as least squares. Remember, ordinary least squares, because we're going to minimize the squared errors. So we have an equation for estimating these coefficients. So the equation for estimating the coefficients when we use this statistical technique is simply minimizing the sum of the squared errors. That's all we're doing. Now, trying to do that by hand would be very hard, but a computer, yeah, this is not a very challenging task. So here's our equation, and I know it looks like a lot, but gang, this is super easy. We have beta hat on the left. We're estimating our beta. And so we're simply saying it's going to be whatever we need to do to minimize the sum of the middle term is just our y minus the right-hand side of the equation. All that is the error term. If we take y minus everything on the right-hand side, except for the error term, we're left with the error term. And then we're going to square it. So if that middle part confuses you, don't worry about it. This is the part we care about. Our estimate for beta hat is going to be whatever minimizes the sum of the error terms once we squared them. And you see that E with the squared sign? We have to square those since some are positive, some are negative. So that's what we're doing when we run OLS. Now, there are some assumptions of OLS. We're not going to go through all of them. But as we said, OLS is blue. What does that mean again? It gives us the best linear, unbiased estimates. And that is if the Gauss-Markov assumptions are met, which are also called the classical assumptions. For the most part, there's actually a slight difference between the two, but this is not something we care about for this class. These can get really technical, and so we're not going to go through all of them, but I want to introduce you to a few of the ones that will help us make some sense of this. So again, ordinary least squares is blue, assuming that we meet this set of classical assumptions. For example, the first assumption says the regression model is linear in parameters and is correctly specified. So there's two things going on there. The model is linear in parameters, and then the second thing, it's correctly specified. So let's start by focusing on the first part, linear in parameters. Now, a parameter is a coefficient. So why do we say parameters here? I don't know. But I could have just substituted the word coefficients, right? Our betas, our alphas and betas. So the regression model is linear in its coefficients. It doesn't say variables, it says coefficients. So guys, can my model have a variable that enters non-linearly, like x squared? Could we have absences squared? Maybe I think there's a non-linear effect of absences. Maybe I think that for each additional absence, maybe the impact gets bigger and bigger and bigger. That would require a squared term. So what's the answer? Can I have a non-linear variable? The answer is yes, because go back to the bold part. It says the regression model is linear in parameters, in coefficients, not in variables. But we can't have 1 over beta, or beta squared. We can't have nonlinear coefficients. You see the difference? We can have nonlinear variables, but not nonlinear coefficients. So our coefficients must be linear. All right, that's the first part of A. The model is linear in parameters. Our coefficients are alphas and betas. Now the second part says that the regression model is correctly specified. Well, what does that mean? Correctly specified. It means it has all of the right variables in it. It has all of the right variables in it. It doesn't have any irrelevant variables, right? We don't want to throw in things that don't matter. Now, that doesn't mean they're not statistically insignificant, but I'm saying things that just don't make any sense to put in the model. For example, in my study of absences and test scores, should I add a variable? Does the student have a dog? I don't think that that's a relevant variable when we're talking about test scores. So I shouldn't include those kinds of things. But I also need to have no omitted variables. And omitted variables are things that are deemed important, but they were left out. So our test score model, right, in its current form, because we simply have absences affecting test scores. Do you agree? We have omitted variables. There are important things being left out. We don't have any measure of ability. Ability probably has a much bigger impact on test scores than does absences. So in our current form, in our simple regression that we've been working with, yeah, we have omitted variables. But I don't think we have any irrelevant variables, which is good, right? So we've only got one variable on the right-hand side. So you get the idea. The regression models linear in parameters, the coefficients, and it's correctly specified, meaning we have no irrelevant variables and we have no omitted variables. All right, that's A. Not too hard to understand. Now, second is B. There is variation in our variables. Now, what we mean by that is in our data on our variables. In other words, not all values of X can be the same. Not all values of X can be the same. We must have at least two values. Remember, X is a variable. So we need our variable to have at least two let me say that again. We need our variables to have at least two values. For example, if absences are the same for all students, if every single student has 3 absences, then we can't use absences to explain differences in test scores. There's no variation that will help us learn how changes in absences matters. I'm only able to generate that kind of information from the fact that students have different numbers of absences. So that's what we mean when we say the second bullet, we need to have at least two variables. If half the students have 5 absences and the other half has 3, all right, I can estimate something from that. May not be as good as if I had more variation, but I can at least estimate that. But if everyone has 3 absences, we cannot estimate that. Now, we can see this mathematically too if we look at the equation for estimating betas. Now, this says beta 0, but it could be beta 1. It doesn't matter. In the denominator of that equation, we have xi minus x bar. Xi would be absences for student I. X bar would be the average absences. But wouldn't that be 0, right? Student I has 3 absences, but if everyone has 3 absences, then the average is also 3. 3 minus 3 gives me 0, and it's in the denominator of my equation. Can I divide by 0, guys? No, that's mathematically undefined. So we have to have at least some variation in every variable of interest. Same thing if we were thinking about test scores. That wouldn't make any sense. If every student has the same test scores, then there's nothing for us to estimate. All right, you get that. So let's look at some simple regression examples. And now we're going to use some numbers. So example 1, let's say we're predicting cases of beer sold based on price. And so we're still in a world of simple regression. We only have one explanatory variable. Everyone agree that beer sold is my dependent variable, right? Price is my explanatory variable. That gives us an equation like this. Sales is a function of price, right? Sales equals alpha plus beta price plus our error term. Note the sub I, which is telling us that we have independent observations, right? And each one of those is a subscript I. So we're looking at cases of beer sold based on price. And so let's say that we go around to a whole lot of different locations, convenience stores, and we collect prices and sales. So in this case, if we go to a whole bunch of different convenience stores, then an observation would be a convenience store. So what is our expected sign for beta 1? What is our expected sign? Do we think it's going to be positive or do we think it's going to be negative? So what do you think is the relationship between price and sales? If price goes up, what happens to sales? Well, in economics, the law of demand tells us that there's a negative relationship between price and quantity. If price goes up, I know you already know that quantity goes down. So does everyone agree we would expect there to be a negative relationship? That means we think beta 1 is going to be negative. And I found this example online, so somebody had already plotted a scatter plot. If we look at the scatter plot, we see that negative relationship. Again, do you see that those observations aren't all sitting on the line? That line is being fitted in a way that minimizes the squared errors. So we have a negative relationship here. All right, so we've put our data into Excel. We've asked our statistical package to spit us out some regression coefficients. And you see here in the red box, I've got an intercept, 1,812. And we have 18 packs price of beer with an estimate of negative 93. So we've just estimated our alpha and our beta 1. So our alpha is 1,812. Our beta 1 is negative 93. So what I'm going to do is plug these numbers in to our equation, but it's going to be predicted sales at this point because this is an estimate. So, like so, predicted sales of beer equals 1,812 minus 93 multiplied by price. And this is beer 18 packs that somebody did a quick little study on. All right, so now we have our sample equation, right? Because our sample equation is after we get our estimates, those things with the hats. And now we have them, we've plugged them into our equation. So how do we interpret this? How do we interpret this? Now, assuming that the coefficients are statistically significant, which they are, but we haven't really talked about statistical significance in our regression results yet, so we're going to assume they are significant, and just jump into interpretation. So what this tells us is, looking at our beta of 93, negative 93, for a $1 increase in price, tell me what's going to happen to predicted sales. When price goes up by $1, sales fall by 93 units. That's the prediction. For a $1 increase in price, sales fall by 93. So, what if price was going up by $2? What does our model say? If price goes up by $2, sales would fall by 186, right? I'm just doubling it. So remember, our beta tells us the effect of a 1 unit change in our explanatory variable. That's why I said a $1 increase in price, because it captures the effect of a 1 unit change, where a 1 unit change in price is $1 here. All right. Now, if these are not statistically significant, meaning we fail to reject our null hypothesis, right? Then we can't say that an increase in price makes sales fall. So right now, we're assuming it's statistically significant, which it is, but it could be the case that Excel gives us a coefficient of negative 93, but it turns out that there's just not enough evidence, and so we can't say that we have this effect. We'll do some examples of that. But first, let's just take a look at this and make sure we understand how to interpret. For every $1 increase in price, sales fall by negative 3 units. That's what the negative sign is telling me. And 93 is our estimate of the beta. Now, we have an intercept of 1,812. And understand that this doesn't really have a direct meaning. Remember what our intercept is. It's where we hit the vertical axis, which means X would have to be 0. So this captures our estimate of sales if price is 0, right? It's our point on the vertical axis. But remember, price will never be 0. So it helps us, we estimate it, but by itself, it's hard to really know how to interpret that, given that price will never be 0. There's not going to be any 7-Eleven saying, hey, beer costs $0. So it's not clear how useful it is by itself. But as part of the equation, it helps us get the right estimates. Now, as stated, we still need to subject our coefficients to a hypothesis test to see if they're statistically significant. And so that's where we're going to do this based on our hypothesis test. So remember what we're doing when we're looking at hypothesis tests. We're testing the strength of the evidence that absences matter on test scores. How strong is the evidence that absences affect test scores? Remember that just because our statistical package gives us a number, gives us an estimate for beta, well, that doesn't mean it's statistically significant. And we want to remember that. So in the example I just did, I said, hey, it is statistically significant because I can read in the output that I showed you that it's statistically significant, but we've not covered that yet in the context of regression, and we will. So we're going to pick that up next lecture, but don't close out yet because we just have a few more slides to go. Now, some of you might have had a class on machine learning, or maybe you were exposed to machine learning at some point in your undergraduate career. Machine learning is an approach to finding patterns in large data, and it can be very valuable, but it's not the same thing as regression, and I want to make sure you understand the distinction. When we look at machine learning, it's trying all combinations of variables, right? It's just kind of going through this automated process where it's trying all different combinations of variables to see which combination has the most explanatory power. And then based on that, it creates forecasts. But that's not what we're doing with regression analysis. With regression analysis, we're trying to distinguish between correlation and causation by seeing if a relationship actually exists. And then remember, if a relationship exists, we can measure the magnitude of that relationship. Is it strong? Is it weak? And what's the direction in terms of, is it positive? Is it negative? And we're not just having a computer go through the motions of trying every single combination. That's our job. It's our job to put together a model that makes sense. So In regression analysis, if we simply tried all combinations of variables without sitting down to think about what the model should look like and what's an irrelevant variable, what would be omitted variables, well, that's what we call data mining. And you've probably heard that term before. And data mining's not good. We don't want to do that. In other words, whereas machine learning, the computer is simply trying to maximize our R squared, which is a measure of goodness of fit. We're not simply striving to maximize R squared like we'd like it to be maximized, but we're instead sitting down with the idea of applying theory or applying logic. It's kind of an art. We have to create sound models, whereas with machine learning, it's just trying every combination, trying to see what sticks. It's not an art form like having to sit down and think about what might really matter in a regression equation. So hopefully that helps you distinguish between that in case you were at all confused about machine learning versus regression. So very quickly, in this lecture, we've looked at simple regressions. Understand that that's a regression model with one explanatory variable. So only an X and a Y. And if we only have an X and a Y, it means we're not controlling for all else that might matter. There could be other things that matter. So in our next unit, we need to add in those other things that might matter by looking at multiple regression. And then we need to figure out how to interpret the results because it will be just a little more challenging in multiple regression, but not much harder. Do make sure before you move on to the next lecture that you understand the basics of simple regression. Otherwise, it might be confusing. So please let me know if you have any questions. Thank you for listening, and I hope you have a fantastic day.